So in this video, we're going to recap the concepts of covariance and correlation and the equations which are used to calculate those. So first of all, covariance and correlation are measuring the direction and strength of a linear relationship between two numerical variables. So remember in the recap video about data types, one of the things we talked about was numerical or quantitative variables. So these can be like continuous variables or discrete variables. These are the ones we're looking at when we're talking about covariance and correlation. The other thing to note is we're looking specifically at a linear relationship between these variables. We're not looking at any other type, quadratic, logarithmic, doesn't matter. We're only looking at a linear relationship between them. So the other key bit to pick out is this direction and strength part. So if you're interested in just the direction of a linear relationship between your two variables, then this is where you're going to want to calculate the covariance for your data set. And if you're specifically interested in the strength, then this is where you need to calculate correlation, and we're going to look at the correlation coefficient. So these are the equations that we're going to go through now. So covariance, the equations for it depend on whether you're looking at population or sample data. So remember that the population data, that's when you've got the data for every single person or whatever it is within your population. Sample data is when you've just got it for a few, and these are meant to be representative of the wider population. So if we look at the first equation, which is when we have population data, COV, that's going to be your covariance that we're trying to calculate so that we can conclude the direction. And X and Y here, these are your numerical variables that you're trying to work out whether they're what the direction is of. So numerical variables. All right, so then we've got our sum of sign, that's that sigma. And we need to take x minus mu x. So x is going to be an observation. Okay. Mu x, all right, remember in the other videos we talked about mu being the mean. So it's going to be the mean of our variable x. Oops, sorry. Y, this is going to be the corresponding y value for our observation that we're interested in. And then finally we've got mu y, which is going to be the mean of the y variable. And finally on the bottom line, n is the number of observations or people or whatever it is in your data set. So I've just popped in some data up here. And as an example, if we wanted to calculate the covariance between x and y, which are these two random variables I've just made up, in here, x and y, it corresponds to each observation as we move through. Remember, we're summing them together. So the first time you do this, x would correspond to the first x, which is 1, and y would correspond to the first y, which is 2. And then it's a sum of, so then you'd add the next time you go it. The x in here would be the second one, which is 3, and the y in here would be 5. Again, we're summing, so we add, and then you do the third one, and you keep going until you've completed them all. So that's just a quick example of how you could calculate your covariance of your population data. So if we now look at what happens for the sample data, it looks pretty much the same. So COV, except just note that we're using lowercase letters here, is equal to the covariance. X and Y are still our numerical variables. X here, again, it's the same as what we had before. So it's the observation. So again, the first time that you look at this, you're going to use the first set, then it's a sum of, so plus, the second time you use this, plus, the third time you use this. X bar here, all right, that's again the mean. It's just that this time we're using our sample data. So remember that when we're using population data, we have all these Greek letters to represent our mean. And when we're looking at sample data, we just use regular letters to represent our mean. So again, y here is our observation, and y bar is the mean of y. On the bottom line, we've got n minus 1, okay, and again, it's just swapping over the capitalization because it's sample data. This is again going to be the number of observations, and we have minus 1 in here because it is sample data. So that's pretty much it in terms of applying the equation. So you can go and look at the examples if you want to have a better idea of how to actually do this in practice. So now if we scroll down, what we were interested in is the direction, okay? So we have a couple of things that can happen. So the first one is that if we end up with a positive value that falls out of these calculations for covariance, then we're going to have positive association, okay? That means if one variable goes up, the other will go up. The second case that we can have is that we have negative covariance. So if a negative number falls out of these equations, then we've got negative association, and that means one variable is going to increase as the other decreases. So let's have a quick look at what this might look like in terms of a graph. So if we have a positive value for our covariance, what we would expect is that the graph between our two variables, we'll call them x and y, the trend line should be going upwards, okay? So if these are our random data points, that should be what the trend line is. However, if I have our other case, which is where we have the negative covariance, we should have a downward trend line for our relationship between x and y. So it should look something like this, and our data points might be all over like this. Okay, so that's what we're looking at. So in this case, you can see that as x increases, y increases along the line. But for this case, we can see that as x increases, the y value here is decreasing, which is what we said for the negative association. Alright, so that's told us the direction that we were interested in. Now the problem then becomes that this value that we get out for covariance, the actual number associated with it is somewhat dependent on the values that you're looking at calculating it of. So if you have really big values within your data points, then you're going to get a bigger value for the covariance. If you have small values that you're looking at, then you're going to get small values of your covariance. So it's not really very informative in terms of telling you the strength or how closely related your x and y variables are in that linear relationship. So that's why we have the correlation coefficient. Okay, so if we scroll down here, so the correlation coefficient, again, it depends, this one doesn't really so much depend on whether you have population or sample data. All that really changes is the symbols this time that we use. So you can see that here, rho is going to be what's used to calculate the correlation coefficient, and for sample data, it's going to be R, which is what we use. Again, that's kind of consistent with Greek letters being used for population data and just regular letters being used for sample data. So let's quickly label these things. So that's our correlation coefficient that we're trying to calculate. Coefficient. Alright, on the top line here, this is the covariance that you would have calculated in the previous set of equations. Okay, you can see we're using the capital COV to denote that we're looking for the population covariance. On the bottom line here, we have some standard deviations. So this is sigma x, that's going to be the standard deviation, for variable x. And the other one is going to be your standard deviation for variable y. Okay. If you're unsure of where to get those from, then go back and look at the recap video for standard deviation. On the other side here for sample, it's exactly the same. So this R here is your correlation coefficient. Oh, can't spell. On the top line, again, this is your covariance. Just note that you want it for the sample since it's the sample data. And then Sx and Sy, that is just denoting the standard deviation again for your two variables. So standard deviation of x, and this one is the standard deviation of y. Again, go back and look at the recap videos if you want to revise where you get those values from. Alright, so if you work out what your value for rho or r is, your correlation coefficient, it's going to be able to then tell you how strong your variables are related to each other. So in the left-hand column here, we've got, this is the absolute value of our correlation coefficient in both cases. That's what these bars are telling you. So absolute value. That just means that it wants you to take the positive version. So if rho ends up being -5, that means that the absolute value of it would be the positive, so +5. Same thing for this one here. So in the right-hand column, we have the interpretation. So basically, someone's come up with some words to describe how strong your variables are related together based on the value of your correlation coefficient. So if you get a value of 0 fall out of your equation, that means that there's absolutely no relationship at all between your two variables, x and y. So that's probably going to be pretty rare. This one here, if you have a value of less than 0.3, you can say this is going to be weak correlation. So that means that the values are probably a little bit over the place, but there is a general kind of trend. This one here, if you have moderate correlation, it's going to be between 0.3 and 0.7. That would suggest that most of the values kind of follow where they should be. If you have a value of more than 0.7, that's going to be strong. So that means that the values are probably pretty close to the linear trend line. And if you end up with a value of 1, that means you've got a perfect relationship. So that means that every value is going to be sitting on the trend line. So let's give a couple of quick examples. So weak, I don't know, if we're looking at x and y, maybe our values are like this. Who knows? Alright, so there is a kind of general trend there, but there is quite a bit of variation. You know, these points are a little bit distance away from the overall trend line. As opposed to if we had a strong relationship between x and y, then we would expect them to all be pretty close to being on the line if this was the overall linear trend line. Okay, so that's kind of the difference, and the others kind of sit in between that. So that's all there is for this video. Take a look at the examples for how to do this in practice, and I'll see you in those.